Welcome to Module 3 of the training RAM Analysis. This model will specifically discuss and demonstrate all the RAM methodology step by step. So as you're going to see, RAM methodology is defined in 7 steps, and the objective is to describe initially in this training this 7 step, and after, of course, we're going in details for each RAM methodology step. Okay, some concepts that we use during the training. So reliability is the success chance that the system has a complete mission with satisfactory function quality during a specific period of time. So concerning reliability, three parameters are important. The first one is the time to failure. The second one is the success or and failure and condition, and the third one is the environment condition. So these three issues define the reliability and of course cause effect on reliability. Failure rate is the function that represents the failure occurrence on time. So as will be demonstrating and discussion during the lifetime data analysis model, we can have constant failure rates, or we can have increased failure rates, or a combination. So as many engineers believe, the failure rate is always constant, and they used to apply such a concept for all equipment, and that's totally wrong. We are discussing that in the model lifetime data analysis. Okay, Monte Carlo simulation is a representation of a real behavior of a system along the time. We are already discussing that. So it's a part of run methodology, very important part of run methodology, and we also give some example, and also carry out some case study with some demonstration, and that will be clear what is a Monte Carlo simulation is about. Important index performs operation availability, percentage of operation time which the system is available to fulfill their mission with expect service quality. So as discussed in the previous model, we can have different level of capacity that system is available. So that need to be careful when we apply this modeling and definition of such index, but definitely the operation availability is the most important index to be applied in a system level. Point availability, another concept that we can see in many studies in softwares, but definitely we need to be careful. Let's compare to operation availability. Operation availability, of course, is the most is the most effective index, but we need to understand the concept of point availability. That's the chance that have system available in a specific time. So since we understand the concept and difference between point availability and operation availability, that will be clear how we need to use operation availability as a performance index. We have MTTF, the expected time which equipment may fail, and mean time to repair, expected time which equipment may be repaired. So usually mean time to failure, mean time to repair. We're also going to see that in some cases the mean time to failure will be really the average of times of failure, but in other cases not. Okay, and PDF, the probability density function, which represents events occurrence along the time, so that can represent failure, repair cost, and so on, as discussion. Again, in the lifetime data analysis model, you get more definition about that. Okay, so let's take a look on the first picture that describes the run analysis methodology. As I mentioned in the beginning, the run analysis methodology are described in 7 steps. The first one is scope definition, very important. We need to define well our scope in order to avoid delay in the run analysis delivery documents and results, in order to save time and resource, and in order to avoid reworking. That's when we not have our scope clear, we need from times to times to update our model and information, and that means the whole result of the run analysis need to be updated. That's not good when you already demonstrate some results to a group of engineers and managers. So you need, whenever we made some modification and it's not expected, we need to again demonstrate the result to convince them again that that's are the best solution that we have, and that is not good. So because of that, the scope definition is very important. Yeah. By the other hand, we need to be aware, for example, when we carry out the design phase, maybe the system changed the configuration, maybe there's no system different uh, equipment type that is modified during the design, and we need to update our run model. But that's not changing the scope, that's changing the design. That's a huge difference. And then, of course, the engineers, the project managers, we understand that the result will change. Okay, so let's pay attention on the scope definition, that's very important. So it's very important to get some PIDs, list of equipment, definitions in order to focus and go forward for the next steps of the RAM analysis without lose time with reworking, because wrong scope definition, lack of information in scope definition. The second step is the most important step of the run analysis, because if the input information defined in lifetime data analysis are wrong or are, let's say, incomplete or uh, not represent the it's not confidence data, let's say like that, the all run analysis results will have impact on it. So we need to be sure that the source of the data that we are collecting is confident enough to avoid um, rework and to have a confident result in run analysis, and that we can use such results to improve the design or support some improvement actions in a plant during operational phase. Okay, lifetime data analysis is a complex methodology needed to put a lot of effort. Not only it's not only a matter of training, but you by yourself need to collect some data and make some analysis. And as much as you're going to do this analysis, more you learn and understand about the statistics behind the analysis. Okay, it's important to say that during the run analysis involve a lot of statistics, but also the experience of the engineers, technicians about the equipment support the result of run analysis. So in many cases, we can justify our choice during the lifetime data analysis based on experience that we have, that we know the reality and we know which function will, for example, will represent best the data that we are collecting. We need to also be sure that we are, after collect some data, we make some filter and select the data that is really be used. Can you really be used in a run analysis? So, for example, if we want to assess the performance of such one equipment component, we need to be sure that we are not in consider failures caused by human error. That's not about the equipment performance. So that's very important when we carry out the lifetime data analysis. We go through the lifetime data analysis in next models, and we will go in details about that. Okay, modeling is the best part of the run analysis in terms of enjoy the analysis, because it is the time that you starting to model your system in a diagram block or in an FTA, but mostly in diagram blocks, diagram, and then of course you enjoy that. That is nice work. You can model, you can see the results, you can change configuration. But of course, don't. My suggestion is don't jump to step 3 without finish the step 2, because since you model, you will not have more patience to put all effort to collecting data and work on it. Step two is very hard step. If you have a data, you need to understand the data, you need to filter this data that you're going to use, and after that, you need to carry out the lifetime data analysis. So the step three is request a very good quality of input, and then to go to step three, is important to have a very finished and well done step two. So modeling is not a big issue in most of cases. In some particular case, the model can be very complicated, but most of cases, most of plants, process plants is clear. We need to be careful also when we are modeling. Uh, if we are modeling the which the production or the reliability diagram block, we want to describe or a diagram block concerning reliability or concerning production, and also which level of capacity we want to model. So that's all impacts on modeling. Okay, also we have a model, a training model that will demonstrate in details the information about lifetime data analysis, the information about RBDs and FTAs. Okay, and after we have our RBDs finished with all inputs, we carry out the simulation. And some information about the simulation, some important recommendation about simulation is that we need to define the proper uh, setup for the simulation, the units of time that you're going to use need to be clear, and the number of simulation we need to be careful, because if we have a huge model and we put a high number of simulation, for example 1000, in some it's better to put 500 that should give the same similar results, confident results, and not necessary to take more time by modeling, by putting but by having 1000 simulation, for example. So I had experience, one of the model that I have in the past, in reality was the first model, one huge model with thousands of blocks, that took hours, more almost one working day to get the simulation results. And then I learned that, of course, that was not necessary to carry out 1000 simulation, because when I run the test for run simulation for 500 simulation, I've got the same results. So some issues are also important about the simulation, and also what's you need to clearly understand the simulation results. What's the different description of availability in the simulation result means, what reliability means, why you get reliability 0 or why you get in your result reliability 100%. Need to understand the effect of a preventive maintenance, the inspection, and so on. Okay, and since you have the simulation and it's clear that the results of the simulation make sense, and you can see, for example, the expected number of failures or the expected number of preventive maintenance or inspection, and if that makes sense, you can go to the critical analysis. So the critical analysis demonstrates which are the most critical equipment in terms of life cycle cost impact, in terms of system operation availability impact, in terms of reliability impact, like number of failures and percentage of failures, or even downtime time or numbers of downtime. Okay, so all this type of index is part of critical analysis and demonstrates which are the bad actors. In other words, the equipment that's more impact in the system. This, since we have this information, we can start to work on the bad actors and then demonstrate and propose some actions. Depends on which phase we are in the design. For example, you can put some reliability requirements to avoid that's the uh, that's the bad actors influence on system performance, or we can also put some redundancies and different preventive maintenance policy and so on. So critical analysis will give the basis to define which are the bad actors, the equipment that's more impacting the system performance, and based on it, we can propose some recommendations. Since we've done the step 5, we have the most of the basic solution for the system by itself. But there are also some assessment that mostly are not under the scope of the run analysis, and that's such cases are carried out and and tested in the step 6, that is sensitivity analysis. In the step 6, we test everything that is not under the scope but can also impact the system. And in some cases, we need to negotiate with project managers, with managers that we need to move forward in this run analysis to test some cases. So these cases are mostly related to spare parts or even the impact of another facilities in the main process plant, the impact of utilities in this plant system. Sometimes it's not under the scope, but is a concern that such impact can influence on system performance, and we need to carry out sensitivity analysis. Okay, so after to go through all the 6 steps, we need to finish our analysis and make a conclusion. And usually in reliability engineering, we deliver a report. But in case of a run analysis, is that my advice is to before to deliver a report, to make a presentation, because all these steps that I'm describing now is not clear for most engineers. How you get this reliability data results in lifetime data analysis step 2, and how is the process of lifetime data analysis, how you model your system, why your system is not a model like the process plant, or is modeled such as a reliability diagram block. So that's the issue. That's when engineers that are not familiar with reliability engineering, they look on a report and they have many questions. So to avoid that and improve the acceptance and understanding of the report, it's advisable to make a presentation about the reliability analysis. What's the steps, clarify all the steps, and put some slides and make it as simple as possible in order to make all the involved parts in a run analysis understand that. So project managers, like engineers, technicians, and so on. Okay, so the conclusion is one of the most important parts is the how you pass the information for other engineers, design engineers, or even maintenance engineers, and so on. And you need to be clear when you write a report and before make a presentation. The report of the run analysis is very challenging. You need to be careful that since you are a reliability engineer, you know many details that the other engineers don't know. So it's advisable to put the report as much as simple as possible with the main results. In the first chapter, you put the results of this that's demonstrates the main objective of run analysis. So you need to put the results in the very beginning, a summary about the results, and how is the system performance predicted by the run analysis, the bad actors, and what you propose to do and what you achieve with that. Based on it, many managers, engineers will be happy, and they understood from the beginning what's the main issue. So after that, if they want to check some details, they go through the report and read the report. Okay, hardly someone reads the full run analysis report, because in many cases they really don't understand the details, even though if you make a presentation, but the result need to be clear. So it's good to put a summary in the very beginning, and after go through all this methodology step and describe how you collect the data, which data is the input for your model, demonstrate your RBDs. The RBDs, another point, if you have a lot of RBDs, you don't need to put all these RBDs through the report. You can put an appendix behind and put only the main system, so they understood the main system in a highest level, and after that they can look on the details how you describe some specific system in appendix. So it's other information that's is helpful when you representing the diagram block. So let's go step by step. Scope definition. So here we can see a water supply system with a level of definition of equipment. And when we get a PID like that, we already have the level of equipment and the level of the run analysis we need to carry out. And then we need to confirm that this run analysis is about the towers, and the towers we concern the fence and the structure of the tower. We are also considering the valves between the water storage parts to the pumps, and in the pumps we'll consider some sensors here, if there is some controls, and also the pump by itself, and the additional valves after the pumps. So that's a very important information that needs to be confirmed. We need to be aware that if we are in design phase, maybe during the design this PID will be updated, and we need to update our run analysis accordingly. Sorry. So concerning lifetime data analysis, what's the main objective from in such analysis is to define for each type of equipment or even components, the failures behave along the time. Okay, so here we can see different PDF. This is the shape of a probability density function. So the most common is this green one, is a normal PDF. That the failures happen in an average time with some standard deviation. That's represent a lot of can be fit for a lot of rotating equipment such as pump, blower, compressor, or even valves. That's if you plot the failure rate here, you have increased failure rate after some specific period of time, and of course you need to perform some preventive maintenance to detect such failures to avoid such failures. But you can also have other representation, for example, exponential PDF, this black one here, that represents electrical and electronic device, or even equipment that have a lower chance that to have failure in the beginning of life cycle in the first 10 years, and this failures like occurrence chance is starting to increase in the end of life cycle. So that's failures related to integrity in static equipment such as vessel, furnaces, towers, and pipelines. So this we are talking about here of corrosion, erosion. That's just this failure mode that happen in the very end of the phase. But and also you can have some project mistake assembling or mistakes in operation that trigger failures in the early life phase that are represented for the log normal PDF. So the main objective of the lifetime data analysis concerning run model is to define what kind of behavior pattern have the equipment based on the data that we collecting in the field in order to represent this behavior of such equipment or components that's enabled during the simulation to represent such behavior in the simulation and get the results. So we will have a PDF for failures as represented here. Depends on the equipment, you can have different PDFs. We need to understand why also we have this PDF, why we have a log normal that's not expected, or even if we have normal PDF with but that's happened earlier than expected. Understand why and be aware that which are the performance targets. That's very important, and then use such data in our model. Another very important issue is when we have a log normal PDF. So log normal PDF is not the wanted behavior of any kind of equipment. So the equipment is not expected to have failures during early life phase. So because of that, mostly when we predict some system performance during the design phase, if we get some log normal PDF from the fields that we are collecting to model the system, we are not inputting our model because in our model we don't want to have this log normal PDF. We want to model the expected performance concerning that we not have early life failures caused for project mistakes or assembling human error or even operation human error during the commission that trigger a failure in the very beginning of the life cycle phase. So log normal is very important, giving us a lot of inputs of the type of human error that we can avoid. Of course, we need to use this information. Then we can also do a sensitive case by using this information to demonstrate that by avoiding this cause of failure, we will have higher performance. Okay, but definitely when we predict some system performance and define some requirements of the for the system performance based on a run analysis, we will not consider the log normal for this definition. Need to be careful with that. Okay, but again, lifetime data analysis will have a specific topic that will be demonstrated the basis for to implement during the run analysis methodology. Of course, we have a specific training that describe all issues involved in a lifetime data analysis. This is not objective of the run analysis training, but is also important topic. Because of that, we have two models. One is theoretical, another one is demonstration that will give the attendees the basis to carry out a lifetime data analysis with the field data that they have. Okay, and of course we have a more specific model that describe not only the basis for lifetime data analysis, but more advanced model that enables you also to model your system performance based on the field failure data. Okay. When you get the lifetime data analysis, mostly many people apply the viable PDF. That's a generic PDF that represents very well most of the failures, and we discuss in details about that. And in this case, we have a Beth curve representation that is defined when we have mixed population viable PDF. So if you use the usual viable, you cannot plot this viable PDF. You need to use the mixed viable that have more than one population. Then you can plot this Beth curve. So it's the first point that we need to be aware. Usually when we apply the viable 2 parameters or the viable 3 parameters, we will get some two parts of such PDF, or we get the early phase going to useful life phase, or you get the useful life only, or you get part of useful life going to wear out phase. Okay, so in this Beth curve, we have three parts of life cycle: early life phase, useful life phase, and wear out. Okay, the early life phase is where the project error or assembling manufacturing mistakes and commissioning human error happen as a cause of failure, and then the equipment have a failures in the very beginning of her life when it's not expected. So you have a decreasing failure rate because since such information are detected as this cause of this failure are detected and eliminated, your failure rate starting to decrease and go to useful life. So the useful life is when your failure rate is keep constant and very low. And we need to understand that in some case for electronics equipment, that is the pattern of such equipment. Failures behave along the time, But for mechanical equipments that have degradation and wear out, the effect of preventive maintenance keeps such equipments in this useful life for a very long period of time. Of course, this is expect that you have very low failure rates during some times, and after some times you have increasing failure rates. Okay, and this wear out phase we need to avoid. And here is when after this time t here, for example 7.9, is when we have the equipment failure. So for mechanical parts that we have wear out degradations, we need to define this point when the failure rate starts to increase. If you are a clear uh, uh, if you are able to define clearly this point, we'll be able to define when you carry out some non-destructive tests or even schedule maintenance or inspection to assess the equipment health condition in order to avoid such failures happen. Okay, so this concept of Beth curve dividing the life cycle phase in three phases is very good to explain a lot of patterns of equipment failures and also to define what we can do to mitigate the equipment failures. For example, in case of wear out, we need to implement some preventive maintenance before that's happened. Okay. So the life cycle analysis represents the behavior of such equipment. So here we demonstrate just a result. So we have a beta PDF. You can see the beta parameters in here. Beta, the variable tree parameters have the shape parameters that's very small here. That represents that asymptotic PDF that have failures in the very beginning of life. The eta parameter have as the value of 0.883 that represents 6% of the failures will occur in the until 0.8 of time, that's year. That is around 9 months. And the gamma represents that during this 1.1 year there will not be any failures. That is why this PDF starting after 1.1 here and not in the 0 point. Okay, and that represents the patterns of the failure for this equipment. That was a furnace, and in this case that's happened because the oil, the type of oil that go through this, that was a distillation plant, the type of oil that go through the distillation plant was not the one that was specified during the design phase. Then this oil have a very a higher quantity of sulfur components, and that cause some corrosion in the early life phase of this furnace. And because of that, you can see after one year that was not any kind of this type of oil was not applied, and after, as soon as this oil started to be applied, they trigger some corrosion, and this corrosion was attacking the furnace. So this type of assessment of the PDF is very necessary. So this is not expected behavior for the furnace. The furnace expect to have a Gumbel PDF, so that means a very low chance of failures in the beginning, and the failures after 10 years starting to have some failures and failure rates increase. But unfortunately, what's happened, but we can learn in that, and of course during our run analysis we can get this information input in the model to demonstrate if we will not change the product that we input in this plant, or even if you not change that's the hardest modification, try to modify the structure of internal structure of the furnace, we will have low performance caused by this degradation here. Okay, so in the end what we need to have as input data is for the level of equipment and components we have. So here we have two furnaces. We have some failure mode definition, coke formation, incrustation, and other failure modes. We have for each one of them some PDF parameters. So we can see here for the coke formation, we have a normal with the average and standard deviation, and also for repair time we have a normal PDF with mean and standard deviation. Okay, that's you can see here. That's this time is out in hours, and for the failure this time is here. This template is the output of the lifetime data analysis that is necessary for the run analysis. So for each equipment that I'm modeling, and if I'm modeling this equipment in failure modes or component level, and each component level I have the failure modes, I will need for each one a specific PDF with such parameters definition. These parameters come as a result from lifetime data analysis. So after I have these parameters, I can jump to the next phase, that is modeling. Okay, so here just explanation that is we always say that it's hard to get historical data, but it's also hard to get repair historical data. So repair data mostly in the historical data are not confident because it's not clear what a specific time was dedicated for the repair. The alternative that we have is to ask for the maintenance specialist about such specific repair of such equipment, and then we can have different two scenarios, optimistic and pessimist. And with this information, we can have define a PDF that gets to both values and model our maintainability. So it's very important to understand, in case this is a case of the vessel, that we implement a lot of steps to come to the repair and after to finish the repair. And then all these times are steps that cause shutdown in the system. And it's very important that we represent the downtime caused by the repair, exactly what we have in the system. Otherwise, our prediction will be very optimistic. For this case, for example, concerning the vessel, if we considering only the repair time, we get 8 or 10 hours. But we see that for carry out the repair, finish the repair, in total we need 8 9 hours, between 8 9 hours and 148 hours. So that's a huge difference in terms of downtime. So, but for to be a realistic analysis, we need to have the real downtime, and to have the real downtime, we need to understand all the tasks that need to be done to perform some repair in specific equipment depends on the failure mode. And since that is clear, we will be able to have the real downtime. So depends the level of assessment that we are doing. If we concerning the equipment level or component level, that will be different, and but mostly in component level, in case of replace, you need to open the equipment. We will have similar times because it's just a replacement, but in case of repair we can have different times, but need to be clear. That's the steps, the most important things that you need to consider: the steps to carry out some repair, concerning the beginning of stop the equipment and the end when you close the equipment is ready to start and operate. And that will give us a realistic information to put in our model, not only the repair time, but the total downtime caused by the repair. And that's very important. And that's very important to have a model, a run analysis results that really represent the reality that's happened in the field. There are other options when, in case of lack of data, to carry out the run analysis, and that's applied in many cases. That's reliability engineers do not have historical data, or they do not have confidence historical data, or they even uh, don't know how to carry out a lifetime data analysis. That's happened in many cases, or they need to put a lot of effort to carry out some run analysis. In case of consultants, a company, that's also a challenge because in many cases, if you carry out a lifetime data analysis, that you consume a considerable time. despite being the important step, one of the most important step of run analysis, many companies or many project managers, they do not want to afford this time to investigate the historical data in a field and collect this data to perform a lifetime data analysis. And because of that, engineers look on standards data. So we have this one here that's a guideline for process equipment reliability data. And we have this in this database, and that we need to be careful. Mostly generic database, we have data, reliability data in mean time to failures, and repairs in mean time to repairs. Repair is fine. Based on this mean time to repair, we can consider a standard deviation, use a normal PDF. That in case of normal PDF, the mean time will be similar to the mean. That's this is the parameter of normal PDF. So we need just to be sure if you really have this time, and this time of each equipment represents all this real downtime, considering the the time to open the equipment, inspect, detect the failures, and as well as to close the equipment. Okay, so we need to check this downtime. But here, for example, you can see for repair a reactor, we need 106 hours. That's, for me, that's is realistic information that we have here. We need to be sure in each particular case. And concerning reliability, most of, as I mentioned, most of these generic data are represented in mean time to failure. So that's a point that you need to be careful, because for uh, rotating equipment such as pump or even static equipment, we don't have random failures. We have in this type of equipment, we have patterns of failures along the time, so we expect to have increased failure rates. So what I'm trying to say is that we can use this MTTF as well as a mean and put some standard deviation. Then we have our increased failure rates in our model that can be anticipated by preventive maintenance that we put in our model. That's the correct approach. We can use this database as a reference, but you need to be careful with to not apply in here the PDF, the random failures for all the equipments and run a simulation, because that will not represent the reality. Okay, and we have one famous database that's Ureda, that's applied for oil and gas offshore facility. And here also you have data from represented by exponential PDF. We have all the data uh, describing MTTF. So we need also to be careful when we have rotating equipment and static equipment, because most of this equipment have increasing failure rate as a failure pattern represented by the PDF. So we need to get this to be aware about that. So that's a complex complete database, have many equipments and information. When you don't have equipment, you can use it as a baseline, but you need to be use that carefully, as I mentioned before, and you can also put some good use of that. What is the concerning Oreda specifically? The main concern is that we need to be aware that most of these database are were built based on offshores in the north of the North Sea in UK, or that's in this case, such equipment have specific environments that's different from other regions in the globe. That's you can also have your platform. You have your platform in South America, in Brazil, or you have your platform in Africa or in Saudi Arabia. So it's totally different condition, and need to be careful with such condition, and need to be sure that's impacts in reliability. As I mentioned, reliability is not defined only by the failure and the failure and the time of the failure, but also by the operational condition. So these conditions are different, so of course we have different reliability dates. So pay attention on it when you use generic data when you do not have the data. Of course, That's a good database. That is a good reference. It helps a lot when you do not have any data or not have reliable data, but also consider the specialist elicitation to confirm your prediction for lifetime data analysis, or even to confirm the data that you're using based on generic data. The specialist is also a good source of information that you can transfer in input for your run analysis. Okay, after you have your inputs, your lifetime data analysis results, or even the PDF parameters defined for a generical database, you go through a model to the modeling phase, and in modeling phase, mostly for process plants, most of the case you model in RBG. So RBG is a logic that represents how the equipment, subsystem and equipment affect the system in terms of failure. Okay, so when we represent some equipment in series, that means if one of them fail, the whole system will fail. If we represent in parallel, need to have the combination. In this case here, both need to fail for the system fail. So we have different configurations of parallel, and we can have more than one equipment in parallel, and then we can have some conditions, such as if you have a tree, at least two need to be available for not shut down the system, and so on. We are discussing details the modeling the RBG in the next model that we discuss RBG and FTA, and I will give a clear information about how does it works and what's the calculation behind of that. Okay. What is important during the modeling that you need to be sure about your model and the impact of each system. So what is I recommend is to prepare the assumption list to RBG model. So the assumption lists are a set of questions that that's defining the type of model that you have. In other words, you have a PID, a drawing that you can look on it, and for each equipment you ask the effect of such equipment failure in the system. And based on such information, you have a document that enables you to model your RBG. So we're starting also to make some question. So for example, here, for how long does the system operate and what is the daily production? So this is very important. Sometimes this information is not in a report, and it's very hard to understand what is real the production, nominal production for these plants. And in this case, in order to avoid mistakes and confusion, you can put in your assumption list this question, and then the designer engineer will answer that, and you'll be able to model and have a document that you can have as a basis for your model. And whenever there are some issue and discussion, you look on your assumption list that was discussed with the designer's engineer. Okay. So another type of question: what is the system lifetime? So how long does the program maintenance there's a overhaul takes, and when and in which frequency this takes? So it's a very usual question for petrochemical refinery plants that we operate for during a specific period of time, 3 years, and after they have a shutdown to carry out a programmed maintenance. So how long does it take? So you can also, that's very important information you put in your model. Okay, and then you start to discussion about specific equipment. So you can see in the question 5, that's we're talking about the tank 01. So what happens if the tank 01 shuts down? Will the system shut down or lose production capacity? So in case we have two tanks, we can lose production capacity, or we have a real shutdown if we have only one tank, or even how long does it take to have this production here. And the question 6 is a question about the pump 1, A and B. So here I'm confirming that's that's the B will shut down. If I lose the both pump, I will have shut down the plant. Okay, and lose 100 of my capacity. And I go step by step, include all the equipment in this list and make this question. What is it? And then in the end, I have the answers to build my RBG. Why is it important to have an assumption list to RBG model? Because the assumption list is a document that support your RBD. So after some months, some years, if someone look on your model and after that there were some modifications in the plant, in the process plant, or even in design, they can understand that this model, your RBD model, are based on a design that is during the design that was the configuration of the system, and the assumption of this model is defined in here, is very clear here, so everyone can understand why this RBD have such configuration if they read the assumption. And reading the assumption list, all engineers will understand the RBD, how does it work. So that's very important to have an assumption list when you're modeling, especially during the design, that you can have change in the system configuration. I had experience in one of my first project that's we had to model a process plant, and when we finish that and present this system for the engineers, one of the engineers opened the question that it's not the design defining, that was not the design defining during for this system. And of course we had this assumption list when we demonstrate that when we are defining this RBD, the assumption and the design was exactly what is represented in the RBD. So that was not a mistake of representation, but that was a design configuration when the time that we model the system. So that was clear that if they need to redesign, if they change the design, and this change need to represent again in the run model, that was not a mistake in the modeling, but was just a change in the design configuration that was not informed to the reliability engineers. So because of that, they did not update the model. And then during that meeting was clear that was not our issue. What we are considering was based on a specific design definition, and if the design change, of course, we need to update our model. And that supports a lot when we carry out some RBD during the design phase, okay? And then when we have finished our RBD, of course, we run a simulation. The simulation here, you can see we need to define some numbers of simulation and get the results. So the model, they got all the RBD configuration, all inputs of each block concerning reliability modeling, and calculate the downtime and the end the average of operation availability. Okay, here start shows that is a block scene software from Relisoft, the simulation. That's the simulation templates that demonstrates the time during the simulation, how long does it takes. And yeah, in the end, if you click in details, we get all the results. Okay, some step that's very important during the model, as I mentioned, is the critical analysis, and we need to be careful in case of production modeling, because in terms of production, we want to know which are the equipment that cause more impact in the production. So here was a case that we are modeling the production, and we have the percentage of loss index, percentage of loss of production, and we can see that this E is E 03, 07, 01, and 04 are heat exchanger that have some failures caused by incrustation due to low quality in the water. It's the dirt water that causes incrustation in the tubes in the heat exchanger. So these four tubes heat exchanger is supplied for the same water, and in this case they have the same incrustation, and you have basically the same percentage of loss of production. Okay, loss of production is very important index, and that's need to be represented in case of you want to model your production, and that type of result need to be represented in this case. We have other critical analysis. Other important one is the availability rank. What this availability rank is about? You put a table, and the table from up to the bottom demonstrate the operational availability for each individual equipment. So the ones are in the bottom are the most critical, that's impacting more in the system operational availability. So if you that's describe if you need to implement some improvements, you need to start from the bottom to the up in terms of criticality, in terms of improvement. That's the equipment, the equipments that need to be first improved in order to increase the system operation availability. And that's happened because if you have, we concern here that all such equipment are in series, of course, and in our RBD, that means if I have failure in one of them, I will shut down the system. And since I have this type of configuration, direct impact on the system, so the system will be lower, the system operation availability will be lower than the lowest value among the equipment operation reliability. So if I calculate the operation availability here, that will be the product with this all operation availabilities. That means 99.87 plus 99. Multiplied by 99.52 multiplied by 99.46 and so on. And this result will be lower than 98.51. So if I decide to increase this one I decided to increase my operation availability. So that's availability rank is a very important information in order to implement some improvement in the equipment. And of course here, when I talking about operation availability, I can check is if it's a reliability issue or maintainability issue. In other words, this operation availability is low because of number of failures that happen in a specific period of time, or because the downtime caused by the repair time, or preventive maintenance repair time. Okay, so that's need to also to be discussion. And then of course, if I look in details in the run analysis, this particular equipment that's represented by a block, I will get this information. Again, sensitivity analysis is an important part of the run analysis. In some cases, we do not consider sensitivity analysis, and in the end, when we have the plants under operation, we not achieve the targets because we have some impact for other system, or even because we do not have, for example, a good spare part policy. So in this case, is an example of sensitivity analysis. In the beginning, I carry out the run analysis for this hydro desulfurization treatment plants, and after I want to see, my intention was to check the impact of another plant in this plants, the main plant that I am planning. So that means if this plant shut down, this one will be shut down. If this hydrogen generation shut down, that this IITT will shut down. And if the cogeneration shut down, this one will shut down. So in the end, I will see the real impact of other plants in my plants and the real operational availability I will get, not only concerning my equipment inside this plant, but also the other system effects. So sensitivity analysis is very important and to assess the impact of other systems, for example, and to know if I need to improve performance in other system in order to achieve my main process the performance that I wanted, and we define it during the design. Okay, so in the end we have run reports. Run reports usually need to have a structure. In the very beginning, need to define the project description, the field schematic, scope of work. Here is very important. So if someone believe that something is missing, we need to they will check in here, and that's defined in a meeting. Usually in kickoff meeting where the scope is defined, but of course during the design and during the run analysis the scope can change, but you need to update that and have this information documented in order to demonstrate that you follow the scope definition. So we have scope of the documents here that's describe everything that you have in details in document. Here definition and terms are very important because many people have confusion about reliability concept, operation availability concept. many people believe that mean time to failure is reliability, and of course it's not. So when you have these terms and abbreviation, that will be clear all these terms, and you need to put the proper definition of such terms, of course. Then you have the references if you got information from another reports. For example, if you have database uh, if you did not carry out a lifetime data analysis but get the reliability and maintainability information from a database, you need to put as a references, books, and other issues here. And then, of course, you start to define the objective scope definitions. Is very important. What you use when you're talking about operational availability, what's the definition of operational availability? What's the definition of production efficiency? And what's the definition of reliability? People have different understanding about such definitions. So in your report, as a reliability engineer, you need to be clear and define how is your definition for such index. That needs to be clear. Otherwise, you believe that different engineers, project managers are having the same understanding, but they have not. Okay, that needs to be clear. So the run study objective very important as well. So for example, sometimes an objective is not just to carry out any sensitivity analysis. They don't care about the impact of other plants or utilities in your process system. Okay, that is need to be clear in the scope, because someone is interested on it, and maybe they will ask during your presentation, or they will questioning your report. But if you define, it's very clear in a run study objective, that will be clear. Okay, so we can also define some run scope exclusion, why you do not consider some issues in a run analysis. The design life of the plant, that's important information that it's come from the design, and the designer and engineer need to check if this information is clear. For example, if the and that's in design documents is very clear how long the plant needs to operate and in which conditions, so on. Run studies boundaries, of course, that's is part of a description of scope or your scope. So you have, since you define your scope, you have define your boundaries. But also it's very important here to define in which level will you model your system. And if you're very beginning the concept phase that you do not have information on the very beginning of the design phase, you're not able to define to carry out a run analysis or in an equipment components level, failure mode level. But even though you will have important information to you can carry out an equipment level or this equipment or subsystem level, and that needs to be defined here in the boundaries. Okay, not only external boundaries but internal boundaries as well. So you put some generic process system, you can put that, the design capacity, the production profile, very important in case of production. So we know in oil and gas, we have production profile from in different cases. In case of platform offshore, we product some platform produce oil, gas, and water. Others produce mostly gas or oil and gas. So the production profile is very important in case of platform. If you have different products as raw materials inputs, you need to put in here. So if this changes from time to time, that information needs to be clear in this production profile. Okay, run inputs study data. So that's about the reliability, maintainability data. You need to put a chapter about that, and then of course equipment modeling. So this was an offshore subsea system. So here are the scopes. So the system that we're modeling, and here we can see a chapter about preventive maintenance task that was considered in this model. So all the preventive maintenance tests defined during the RCM analysis, and we are including here, and then one specific chapter about reliability and maintainability data. So how you get that data source, and of course reliability and maintainability data here again. So we have your reliability and maintainability data for each one of the equipment, then your run model, and so on. So that is the end of this model. The objective was to demonstrate the complete steps of the run analysis. We go in detail if for each one of such steps and define clearly, and you understand clearly about what is about to carry out a lifetime data analysis. That will be two models that we explain that. We have two models as well to explain the RBG and FTAs, what's the difference and what is the concept behind that. Then we move to starting to make some model examples, and after we, of course, we will have more detailed information and assessment and modeling concerning run analysis. Okay, so thanks to attend this model. If you have some question, just send me a mail. Most of the information here will be clear in the next model.